Remind me not to pick a fight with Bipul and the VCSELs. And also the micro LEDs. We will stay away from both of that. Actually, I'm going to take a slightly different tack. I'm actually going to talk about, people draw drawings of 2D integration, 2.5D, 3D integration. I'm actually going to talk about technology development that needs to happen to actually realize these things. It's easy to draw block diagrams, but it takes a lot to actually realize this. So I'm from Marvell and from the Cloud and Cloud Optics Business Group. Actually, you can ignore the statement. First, we just want to look at 20 years of data center, actually, pluggable modules. For those of you here, as old enough as I am, maybe we'll exclude Chris, it looks always young. Starting with a GBIC in year 2002, a gigabit was a watt. So for those of you who remember, a gigabit per watt is 1,000 picojoules per bit. Over the last 22 years, this 1,000 picojoules per bit is today at about 12 picojoules per bit, or 13 picojoules per bit, depending on who you talk to and depending on time of the day. And within the same 20 years, the data rate has gone up by 3 orders of magnitude, and the picojoules per bit has come down by 2 orders of magnitude. It's only the efficiency has come down, guys. Modules consume more and more power every day, and the missing 1 order of magnitude in this math is just the power going up. But these have made remarkable improvements. And these improvements didn't come easy. Electronics, optics, and the combination thereof. But the energy consumption has gone down pretty interestingly all the way down, and there's an expectation it will continue to go down. We might be hitting some roadblocks, maybe, as the data rate per lane goes up. Don't want to get into that today, but I just want to show a couple of things and focus on making light engines. So that way I stay out of trouble. All right. You take a module. This is known. We published it a couple of years back. And you break it apart, and you look at the power consumption. Of course, there's this 10, 12% overhead that you pay. They're tunable lasers. This is actually a breakout for a ZR module, but it's the same for whether it's a PAM4 or a ZR with a DSP in there. Optics, electronics, about 27%. A DSP, about half the power. And if you thought we were just making these numbers up, there's a commensurate publication which happened at about the same time frame, which breaks out in a little bit more detail. We have the breakout too, but this is not the talk. But half of it is the SerDes, so half of it is the optics and the DC-DC conversion. So you could argue, what I'm going to focus on is that 50% that we actually have control over, not discussing DSPs, but just looking at linear optical engines. Essentially, what that would be is if a TIA, a driver, maybe a laser, and a silicon photonics modulator, or in this case, a germanium detector. So this is actually what a transceiver is. We talk about transceivers all the time, but if you excluded the host and if you excluded the host on both sides, it's essentially 2 amplifiers, which could be 1 chip, by the way. People build it out of silicon germanium or CMOS. And in this case, a silicon modulator and a germanium photodetector and the laser that could be integrated. There was a talk from Quintessent where it was integrated and the others which were external. I'm going to show you an option where it was integrated. All right. Little clarifications and nomenclature. I do my best PowerPoints in squares and circles too. 2D integration, what I'm calling 2D integration for the purposes of this talk is we're using the silicon photonics chip as the interposer. Remember, everybody uses a silicon as an interposer. Why not just use silicon photonics as an interposer? It puts out light. It's great. All you need is a TIA driver and a DFB laser. In this case, we didn't co-process it. We attached a fully functional DFB laser. And then you can drop it onto an organic substrate with a host ASIC, whether it's a DSP or something else. And I've chosen to call it 2.5D, which we would discuss as well, and then a 3D, which will have the EIC on the optics and the TIA and driver and the stacks going all the way up. As you get to smaller and smaller geometries, you need that. One of the reasons for doing this is power consumption, by the way. We can't afford to wire bond our way out of problems like we tend to do these days. And for those of you who are familiar with this nomenclature on the silicon side, one is chip on wafer. It's not limited to the things that TSMC puts out. It's just a generic name. And then there's a chip on wafer on substrate. That's what CoWoS actually stands for. But you can get these things done at any number of partners out there. All right, now that we have established a baseline for what I'm going to talk about, let me show you how this is done, how it was done, and how we're going to do it. This is how traditional transceivers are packaged, actually. Even if we had a DSP coming down on a BGA package, I picked TIA as an example. You wire bond, a driver is the same. You wire bond to a TIA, and then you wire bond it to a silicon photonics chip or an EML or any number of optical components. And you still do that for EMLs, by the way. And then the next step would be, can we actually integrate this TIA directly onto a silicon photonics chip, come down to one wire bond. That's how our first generation was done. And then the next question is, get rid of wire bonds completely. Can we do TSVs? And you can do TSVs on both the electronic chip or the optical chip. And the case I'm going to show is the optical chip. And you don't really have to do TSVs as another technique in which you can flip chip the silicon photonics as well. But I'm going to just pick one example and show you how it's done and how it could be done. All right. What does this thing look like in practice? And that's exactly what it looks like. If you were to go look at the cross-section is the TIA and driver cross-section. And then you have this thin sliver of silicon photonics. It has to be really thin, about 100 microns. And then you have a TSV. And then you have a bump. And then it goes onto a substrate. This is actually a product. We built it, and it's you can build all these things, and it's a clean cross-section through. And after that, you see vias through multiple layers of organic substrate, and then you have the core, and then it goes to the back of the substrate. To do something like this, a TSV-based optimization is completely non-straightforward. We've seen a lot of people proposing these things, and once you attempt to do it is when you find lots of interesting problems. So the core of this is integration of silicon photonics interposer onto a high-speed substrate. But what's even more important is integration of electronics and optics onto a silicon photonics interposer. This is back-end process, so we don't have to go to a foundry. This is what's important because you can go to the foundry and say you want to do a via middle process. And that's a luxury in a lot of foundries. If you really wanted a via middle process in a silicon photonics foundry. But if you had the wafer and you went outside and had somebody else do the via last process, it becomes a little bit easier. It's going to take quite a bit of explanation, but it's OK. First, you build a silicon photonics wafer, and then you bond it to a carrier wafer. And then you thin the silicon photonics handle. You do the via. And it's still the same carrier wafer, and you build the signal vias, and then you build the bumps at the back. So what this allows you to do is decouple the silicon photonics foundry with an OSAT foundry. So what actually happens when you build something like this, and you actually slog through all of it? This particular case was an 8-inch wafer. That's a wafer level assembly. You can do this at the wafer level. You can do all of it at the wafer level. Takes a lot of work, but it can be done. But the next question logically is, that's a light engine up there. So wafer level assembly, you have a light engine with a TIA and a driver and a DFB on a silicon photonics chip. And you actually have a light engine. We have an entire conference here talking about light engines, and that's what it looks like when you actually build it with external components. The TIAs, what this allows you to do is allows you to independently optimize TIAs and drivers, both in this case for silicon germanium technologies. You can build them out of CMOS if you wanted. And then build the silicon photonics chip in a completely separate foundry, and then go have it assembled in all the well-known ecosystems that exist out there, primarily Asia these days. And what can you do with a light engine? This is when you start picking a fight. We are not advocating one or the other. You can take the light engine and build an LPO module. Seems to be the hot topic these days, so I didn't want to leave that out. Or you can take the same light engine and build something more exotic, right? You can put DSPs on there. You can put microcontrollers on there. You can put anything you want on a substrate, right? Once you have a light engine, the light engine can pretty much go anywhere you want it to. And that's exactly the point. We put it together with a DSP chip, and then there's a optical sort of a connector. It's actually a pigtail at the other end, and this particular application was an FR4 application. A light engine by itself, depending on the power of the DFP, is fairly distance agnostic. And as I said, I'm not going to pick a fight with the VCSELs, so let's call it 100 to 200 meters. It'll work. It will replace rack-to-rack interconnects, and that's the whole goal. We are not hoping to solve the very short reach because there is a compelling need to solve some of these at the rack-to-rack pod level. And of course, if you had a switch, you can integrate it onto a switch. In this particular case was a TL7, integrated optical modules with a switch. And of course, people in the audience will ask, did this thing work? Yes. This is what we call a snake test. We ran it on a chassis, and in the end, you really have to squint to see there's 5 kilometers of fiber that we tagged on, so that there's to show you there's enough margin on some of these things. So as I said, this is more of a capability talk. How do you achieve some of these technologies? How do you integrate them? But this light engine could be integrated onto any number of hosts. And the light engine by itself, it's very simple. It's optics plus 2 electronics and a laser, and you can take that and drop it onto a much larger substrate if you want it and if the application so demanded. Thank you.